Hello and welcome back to my Commodore 64 Technical Peaks video series. In this video, we're going to be talking about and developing some software for how to write a sprite multiplexor, how video displays work, the raster timing, video chip updates, sprite duplication, more complex sprite patterns, and sorting algorithms. This is going to be a very long technical video with lots of source code. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel or sending me a super thanks. They are always very much appreciated. The first thing is some background in how graphics displays worked on the Commodore 64 and Commodore 128. The home computers would drive a video signal to the external display, usually a screen. It would scan from the left to the right and then move down one line and then scan left to right, a lot like you can see with this video display here. If you were in the PAL regions, it would do this roughly 50 times a second. And if you were in the NTSC regions, it would do this roughly 60 times a second. The video chip on the Commodore 64 was the VIC-2 chip, and it would generate all of these signals, and then the display would decode these signals. If we speed up this emulated scanline display, which is very low resolution compared to the much higher resolution on the Commodore 64, we can see as it speeds up that we start to get what looks like animating frames. And we have this little dancing Clyde to show this effect. The image is visible because of persistence of vision and also persistence of these phosphor dots on the cathode ray tube, the CRT display. The Commodore 64 VIC chip allows us to read the vertical raster position, and the raster register in the VIC chip is actually described in the programmer's reference guide, which you could get with the Commodore 64. Scrolling down to the right page in this very, very large PDF file, we can see how it was originally described. It would just tell you the 8 bits plus another 1 bit for the most significant bit, the vertical raster position synchronized to the display. The display synchronizes to the signals for the video signal from the VIC chip. The VIC chip does not synchronize with the TV or the display. The display synchronizes with the VIC chip. This means that the Commodore 64 and its internal display chip, the VIC chip, is updating this register. We can read this register from BASIC, but BASIC is usually not that fast. It's much better to read this register with machine code or latch this register with an interrupt, which the programmer's reference guide says you can do. We can update the VIC chip display registers actually very rapidly. And if we look at the programmer's reference guide, it gives us the address to calculate for updating, for example, the screen color or the border color. We can test this theory with updating the VIC display registers rapidly in synchronization with the raster register position by doing some machine code. So we will turn off all of the interrupts with the SEI instruction. We will load D011, which is the vertical screen scroll Y register, but also the most significant bit of the raster position. We will just do a little positive and negative check there just to make sure that we are starting right up at the top of the screen in terms of raster position. So we want the most significant bit to be cleared, and we'll just do a positive and negative check just to make sure that we're really on the correct portion of the screen. Then we'll set the screen to be black by storing 0 into D020 and D021. We'll then compare the raster register at D012 with the value of 10, and then we will increment the screen and border, or the border and screen registers, rather, D020 and D021. We'll then wait for raster position 70 in decimal there, and again increment the border and screen registers. We'll then wait for raster position 120 in decimal this time by comparing it with the raster register at D012, and we'll loop around until that value is reached. Because we've turned off the interrupts, we can pretty much safely wait for the raster register using a compare and branch instruction, and we'll increment the border and screen colors again. We'll wait for raster position 200 in decimal this time, and we'll increment the border and screen colors. The raster register is 0 up at the top of the screen, and it increments by 1 for every raster line down vertically. And then we get these horizontal bars with some flickering colors on the left-hand side there, and that's just a timing update issue. But generally speaking, we can show that this code successfully waits for specific raster line positions. And if we enable the full debug borders mode in the emulator, we can see that waiting for raster line 10, where the white color starts there, shows about 10 pixels worth of black. And that's because we have the wait for the top of the raster position to reset the screen and border color to be 0, in other words the black color, before incrementing to white and then red and then cyan and then lastly purple. This means that as the screen raster position scans from top to bottom, from left to right, we can precisely time updates to the VIC chip to get these different effects to happen for changing the color. And because we're changing them rapidly enough, the screen, as it's drawn from top to bottom, from left to right, maintains the values that we specify into the VIC chip registers. This is a very quick and simple demonstration of timing raster updates with the VIC chip. I just copied information from the top of the screen for character screen to the rest of the screen, so you can see that actually there's text there. It's not just the screen being switched off or anything like that. There's actually text in front of the background screen and the border colors that are being displayed there on the screen. Let's save this example machine code to a temporary file so that we can actually load it into a different emulator. I'm just saving the bare minimum amount of this from the start at C000 to C049, right, which is at the end of the jump instruction there, which loops back to the top of, or to the near to the start of the example code. Now, if we open this in C64 Debug GUI, which is one of the tools I regularly use in my videos, and then load this code, and then we can start it with sys49152, which is starting the code at C000 that we just created in Vice in the monitor. Then we can see that we've got the same code, same display of these different colored raster bars. They're called raster bars because the color bars are synchronized to the raster vertical position changes. As I scroll or move the targeting cursor up and down in this VIC debug mode here, we can see that the screen reflects the different current border and screen color register values. And as I move it up and down, we can see how those values change depending on the raster position on the screen. As the raster scrolls down, or as the raster proceeds down the screen, as long as the updates are synchronized properly from frame to frame, then we get a consistent raster bar effect on the screen. It's not just limited, of course, to color changes. In the programmer's reference guide, it actually says that up to 8 sprites can be maintained by the VIC chip, but more than 8 sprites can be displayed using raster interrupt techniques. Even when this programmer's reference guide was being authored, they already knew that the VIC chip was capable of displaying more than 8 sprites if you write extra code to update the sprite registers at appropriate values. So just as we can have more background colors being displayed by updating the background color registers, we can appropriately update the sprite pointers to have more than 8 sprites visible on a screen. Or, in putting it in other terms, to reuse sprites or position them as the frame is being drawn. The programmer's reference guide contains all of this extra documentation to do with how to enable sprites, how to change sprites' colors, and how to change sprites' frames as well. So we can use all of this information to update the example code so that instead of just updating the border colors and screen colors, we can precisely time updates to sprite positions to get this single sprite to be displayed in 2 different areas on the screen by using a bit of machine code and precisely timing it. So imagine for the moment that the Commodore 64 only has one hardware sprite. So we've only enabled one hardware sprite here by poking 1 into the appropriate VIC register for sprite enable. Okay. To really show that it's really drawing a sprite, let's just fill that sprite memory with a repeating pattern of 10101010, which, when we look at the sprite, we'll see a repeating pattern of vertical white pixels in high resolution mode. Okay. Now, updating the machine code, we can have this sprite at that position up at the top of the screen when the raster starts coming down the screen. Underneath the sprite, we'll then move the sprite down and we'll display the sprite at a different vertical position. So we'll load the previous demonstration code because it gives a good point at which to start editing this code, okay? And we'll just add in, because the sprite is already visible and because the sprite has already been enabled, we'll just appropriately tweak or change the sprite Y position register for sprite 0 for this sprite that we've currently got visible. So we need to figure out where to put that sprite Y position update code in, and what we'll do is that we'll start putting it in here in the code where we want to update the sprite Y position. So we need to update the sprite Y position at least twice for this frame. We'll update the sprite Y position to set the sprite at that position on the screen that you can currently see it above the sprite. So at the beginning of the frame, roughly. We'll start putting this code at C00B. So we will put 80 in decimal into 53249 in decimal, which is the sprite vertical Y position. Now we're doing this sprite Y position setting right up at the top of the screen, then waiting for raster position 120 in decimal. Thinking about it, we will also set the screen to be, screen and border color to be 0 as well, which is black. Then we will wait for raster position 120. And then we will set the sprite Y position to be underneath position 120 in decimal. So we'll make that position 130. Whoops, I forgot to put a plus to make it a decimal value. It thought I was trying to use a hex value. So there we go. So up at the top of the screen, the sprite Y position will be 80 in decimal, and at position 120, raster position 120, will set it to be 130. So we're moving the sprite rapidly every frame twice. We're putting it up at the top, and then we'll put it down at the bottom. And of course, the sprite is white, and the screen and border color is white. So let's change the sprite's color so that the sprite is a different color other than white. We'll just double check this in the programmer's reference manual. There we go. It's 53287 or D027 in hex. We'll just use the monitor to poke 532 in decimal 87 with the color 2, which should change the sprite to be red. Okay, and then we go back, and there we go. Even though we only have one hardware sprite enabled, we have two hardware sprites visible on the screen. The change from black to white is where we are setting the sprite's Y position. And the sprite's Y position is set to be 10 pixels underneath that black to white split there. And then up at the top of the screen, we're resetting the sprite's Y position to be up in the top half, in the black area. So this is a very, very simple example of how we can duplicate a sprite, one hardware sprite. Let's open this code in C64 Debug GUI now, so we can actually visualize the same single hardware sprite being visible in two different areas on the screen in the debugger. Duplicating the same pokes as before to enable the hardware sprite in the right area. And of course this poke is not the correct poke for enabling a single hardware sprite. It should be 53269. There we go. So we have our sprite there. Let's load that previously saved example code now, and then let's start it again with sys 49152, not 59152. That would have crashed quite spectacularly. Of course, the sprite is white. Let's change that to be red in the debugger. Now we'll just concentrate here on the raster targeting cursor. So we have the sprite there, and then at this position here, we flip the sprite position, Y position, into a different position on the screen, and then the sprite continues to draw. I've used the debugger here to override the sprite color to be red so that we can see the red sprite against the white background of the screen. So this is just a visualization in C64 Debug GUI where we can see where the sprite register updates happen. The same sprite, the same single hardware sprite, is visible in two different areas on the screen. Now this is an example of sprite duplication, but conceptually it's basically what multiplexors do, is that they use the same hardware sprite, but at different positions, different colors, and different sprite frames, or different sprite pointers or graphics, or however you want to call that effect. For the next part of this video, I want to go into more manageable and updatable source code, so I'm going to take a copy of my blank project comp folder, or parts of it anyway, and copy these files to a new working directory. The reason why I'm doing this is that I just want to have a more comfortable code editing experience than using just the monitor in the Vice emulator. I want to have a better text editor. I want to be able to use an assembler to edit my assembly or to assemble my assembly program, and I want to be able to provide source code for you as well so that you can review it. So I need to have the source code committed into my GitHub repository, and of course I will be providing the link to all of this source code and all of these debugging notes and everything else in my GitHub repository, and I'll put that link in the video description below. Here I'm just updating the Visual Studio, Microsoft Visual Studio project file. I'm just renaming all of the occurrences of blank project comp to be HTWAM, which is how to write a multiplexor. And I usually use a build it batch file to call the assembler. Here I'm just updating the Visual Studio solution file, and the solution file references the project file. I tend to use Microsoft Visual Studio because I'm very comfortable with its text editor. I find the IDE text editing framework to be nice, and it also means that when I'm editing C or C++ code, for example, then I can update those C and C++ project files along with my Commodore 64 assembly files. So I'm just updating this code here. I'm going to strip out most of this, although I'm going to keep some of the initialization. Like most of my projects, I make use of pre-written standard library functions, for example, that I've built up over a long period of time. These standard library functions and macros and everything else provide tried and tested, so for example, machine initialization functions. They provide to me nice, consistently named variables, or labels rather, instead of having to remember things like vic chip registers and SID chip registers and stuff like that. I use proper label names because I think it helps make the code more readable and maintainable, and certainly more accessible. Because instead of just having, say, for example, D020 magic values everywhere in the source code, they'll be called things like Vic2 border color or Vic2 screen color, for example. So for me, having consistent label naming and having verbose descriptive label names allows for much more maintainable and understandable code. So I'm just updating now the build it batch file to basically assemble the htwam.a file, which is how to write a multiplexor assembly file. The assembly file has all of these directives for writing the PRG file, writing an LBL file, which is a label file, the map file, which is a map of addresses and labels. Also a PDB file, which is a program database file, which has lots of extra debugging information for how memory addresses map to source code and line number. It also produces a map of free memory and used memory at the end of the PDB file. These are all extra files which are provided by the updated version of Acme that I also include the source code for, of course. The PDB file, the label file, the map file are also usable by debugging tools that I've also been developing over the years to help make assembly language programming on the Commodore 64 or the emulated environment a lot easier, because being able to easily maintain and debug programs makes it easier to develop those programs. And if you have an easier programming environment, then it means that you have to remember less and spend less stressful time remembering a whole bunch of stuff when you are able to easily assemble and quickly assemble your code and then test it and then see how it works or doesn't work. So I run the build it batch file, or I can press the F7 key from Visual Studio, for example, if I have the project open. And then it assembles the code. It then uses the LZMPI compression tool to generate a compressed self-extracting or self-running program file of this, which just basically compresses all of this extra file. So all of the code, all of the data that's in the assembly file eventually gets compressed, and it just makes loading into an emulator a lot more portable experience because you can just send that program file. So now I've opened the solution file and project file in Visual Studio. I'm just removing the old source files and I'm adding the newly named source file I pressed F7 and I just made sure that it assembles. Of course, it cannot start debugging a PRG file. I actually have to set the debugging options now so that it will point to the version of Vice emulator that I use, which is this. I'm just copying that from one of my shortcuts. The dash remote monitor is going to be important, but it needs to be a command argument. There we go. And then we will just, because we're running it from the working project directory, that's okay. We will then just add the file name for the PRG file that was just generated, which is how to write a multiplexor.prg in htwam.prg. And there we go. I'll press Control F5 and then it opens the Vice emulator and then runs the code that was just assembled after pressing F7, which is the build project key. So now I have this easy way of assembling the code and running the code. I also want my nice easy way of debugging this code. So I have my Vice PDB monitor, which is an external tool, which I explain in more detail in the tools video, which I will be adding a link to. But basically, in quick summary, this Vice PDB monitor reads the debugging information from that PDB file, which is output by the Acme assembler, and then it will connect to the Vice remote debugger network port. And it will allow me to, once I run Vice, this will automatically connect, and then it will stop at a breakpoint. It will let me view the source code or disassembly. It will allow me to inspect the machine state. Without using the Vice monitor directly, it connects to the Vice network monitor. So you can see if I switch on the disassembly view and switch it off, well, at the moment the disassembly view is switched off, and that's because it's somewhere in the kernel startup. Okay, so I put a breakpoint at 400, which is the start of the code, and then I click go, and then now I've got the source code disassembly enabled. It's showing where in the source code 400 in hex in the memory view actually is, and it's correctly showing that it's the start of the assembly code. It's showing that it's running SEI, it's running the load accumulator, and then it allows the JSR to be stepped into or stepped over, for example. I can show a dump of all of the label values if there is any memory associated with them. If I step over the JSR, then it's no problem at all for the debugger because it uses the step over functionality in the Vice monitor itself. And then it goes into this code, which just does the increment border color. So this way of developing, assembling, and debugging with source code view assembly language programs is a lot more comfortable, a lot easier than trying to debug opaque binary disassembly of the machine code actually, just in the monitor itself. If I use the label .bph, which means breakpoint here, for example, I can use that naming convention for labels to automatically create a breakpoint in the Vice PDB debugger application. So if I assemble that and then I run it in the debugger, but also a good example of easy code editing is if I put in the pling error command to introduce a forced error, then assembling it will show the error in Visual Studio, and I can press F4 to take me to the error. I don't have to scroll around the line or anything, to scroll around the source files to find it. It will show me where the assembly error is. Anyway, so now I've loaded the new debug session. You can see that it's automatically put a breakpoint now at 400, which is where the .bph label is. And it just allows me to more comfortably and more easily assemble and debug and iterate faster on creating code. The label file has all of the labels that are defined during the assembly for this, and because I'm pulling in a very large standard library assembly file, it creates all of the labels, or it has all of the labels in it for all of the kernel functions, for all of the VIC updates, all of the SID chip updates, and all of the CIA chip updates. And all of the support routines as well that can be optionally pulled in. It also includes label definitions for those and macro definitions for those too. The map file contains a differently formatted map of all of the labels. But anyway, this is a nice, easy to use way of developing programs. You can see here that in the PDB file, if I scroll down to the bottom, it's got a free map. So memory from 0 to 3FF is free, and memory from 4A6 all the way up to FFFF is free. It knows what memory is used and free because it knows where the assembled bytes go to in the memory map. And because there isn't much code, of course, most of the memory is going to be free. Anyway, so now we have this nice empty skeleton project, if you like. We can start adding code to reproduce the duplicated Sprite demo from before, but we're reproducing that duplicated Sprite demo, if you like, in the new code, in the assembly code, rather than the Vice monitor. So we don't have to keep on coding assembly language by hand in the monitor. We are now editing the code in a nicely readable and understandable, or more readable and understandable source file. So we'll use this macro mSetSpriteXY col frame macro. Underneath, inside the macro, you can see that it basically updates the X and Y position. It updates the color, the frame of the sprite, and it also appropriately updates the sprite frame pointers in the appropriate screen related control registers that the VIC chip reads. These registers for the sprite frame usually live at 3F8 hex bytes from the start of the currently displayed text screen mode, or the screen that the VIC chip is accessing at that particular point on the scan line, on the raster position. There are various different tricks that you can use to update these sprite frame pointers, but we won't go into that in too much detail. All we're doing is, at the moment, we're just waiting for a particular position, the raster position on the screen, and we will just use this macro. But I think we'll use a for loop. There's a little typo, there we go, pling for. So we use the pling for pseudo opcode, which is a pseudo opcode that the assembler understands, the Acme assembler. It understands this, and it allows a block of code to be repeated for a number of times that you specify, and also you can have an iterator label, if you like, which represents the number of times it's going through. So this .i label internally in this for loop here, it's not really a loop, it's just expanding code 8 times. The .i label will contain the value from 1 through to 8 inclusively. And you can see there that I've forgotten to put the little positive, negative check in for the most significant bit for the raster position. So what we'll have to do is that I can optionally use one of these wait for raster macros as well. You see, so I can wait for raster position 10, and I'll only increment the border color when updating the block of sprites. So I'll clear the border color to be black up at the top of the screen. There we go. I've even got a label for black, you see, and there we go. So we've got black up at the top of the screen, and then we have white coming along at raster position 10, which is what we expect. Now, because we're in PAL mode, of course, we have the most significant bit for the raster position being set as well. So it's possible to read in the lower 8 bits of the raster register raster position 10 again, but it's not. It's raster position 10 plus 256. We need to of course, remember to put in this code for waiting for positive and negative values for the most significant bit for the raster register. There we go. If we run that now, then we only have one white bar now on the screen where we are updating the values for all 8 sprites. I think what we'll do now is that we'll actually add some proper sprite graphics. So we'll use the sprite line macro to put this sprite definition for the sprite graphics actually at 3FC0, and we'll update and we'll use that sprite in the sprite macro there. But maybe we should skip ahead a little bit and actually add in 8 different visible sprites so that when we're trying to really visualize what the hardware sprites are doing, we'll make sure that the hardware sprites have different visible frames for each of the sprites so that we can differentiate between them. So we need to make sure that we're pointing, first of all, at 8 different sprites. So we'll start having different sprites at not 247, it's going to be 248, of course. There we go, 248. And then if I run that, then we'll see that we've got those sprites there. We'll then use values from 0 to 7 in this for pseudo opcode block. Now we'll simplify this a little bit so that we don't need to have .i-1 everywhere. So now we've rebased the loop count from 1 to 8 from 0 to 7 now. So we use those values appropriately. Now we have a whole bunch of sprites, but we're not filling in all of the sprite graphics definitions or frames for each of the sprites. So we'll just duplicate these sprite lines so that we have 8 different looking sprite graphics now. So this is number 2. We'll just do number 3 and 4 and 5 and 6 and 7 and 8. But I'll do this very quickly. Each sprite needs to be aligned to 64 bytes in decimal, so we'll put an extra byte in after each sprite definition. So sprite line doesn't add the alignment for you. You have to remember that you've got to align it properly in memory. And now when I run this, we'll see that each sprite looks different. I think it would be easier to see that each sprite looks different if the background is cleared rather than having the visible machine code in memory in the screen memory. So what we can do is that we can quite simply, I think, well, what we really want to do is that we want to show that sprite duplication is working as well, right? So we'll wait for the raster position. We'll then duplicate that block of code which sets the sprite definitions, all 8 of them this time. But we'll change the visible aspect of the second row of the sprites. So that's the first row, and then the second row of sprites will duplicate the sprite definitions, the sprite visible sprite frames, but we'll change them so that we'll wait for raster position 110, but we'll put all of the sprite positions at 120. Okay, so now we have 16 sprites duplicating the sprites from the top to the bottom. But we'll also demonstrate that we can change the frame. So we'll reverse the order, if you like, of the colors and also the sprite frames. There we go. This is really starting to look like something there, right? So instead of from colors from 1 through to 8, it's actually showing colors from 15 all the way back to, what was it, 9 or something like that. 8, rather. If we load this code now in C64 Debug GUI, we can see how those 8 duplicated hardware sprites are now visible in different Y positions at different screen positions as the raster scrolls, as the raster proceeds down the screen for every frame that it's drawing. This is an expansion upon the previous demonstration where just one single hardware sprite was being duplicated in 2 different areas on the screen during the frame. We're now just doing it with 8 different sprites with different colors, different sprite frames, different graphics basically. We can also show this effect with different horizontal and vertical positions as well, different X and Y positions on the sprite. But we can see how the code up at the top of the screen moves the sprites up. There we go, each sprite. Because we're just basically doing very optimized code, we're doing a whole bunch of loads and stores, then it doesn't take that many cycles to actually update the sprite positions and frames and colors and everything else. And then we move the raster down the screen, and then at that point on the screen, the code then starts doing all of its sprite updates for the next row of sprites. And you can see that that update code finishes before the next row of sprites needs to start being rendered. That's going to be very, very important later on. So it's very important to not try to update the sprite registers as the sprites are being drawn. We'll see what happens in a bit, I think. I'll try and demonstrate that for you, because this is what multiplexers have to try and avoid. Otherwise you get visual glitches. At the moment, with this kind of simple sprite duplication, we don't need to worry about it so much because we control very tightly the sprite positions and the timing of this code. But sprite multiplexers need to be more flexible in this regard and need to be more aware of this. Before I forget, let's change the code start address to be 800 in hex. I changed the entry point for that code in the compression tool to also be 800 in hex. And we'll use the assembler, I think, to just clear the screen memory. So we know that the default screen memory is at 400 in hex. We'll just fill 40 characters across and 25 characters down with the space character. Now we have an empty text screen, and then we have the code after it. And now we can see that those sprites are visibly a lot different. We can see that the colors are different. We can see that the sprite graphics frames are all different for the top and bottom rows. So even though we're doing sprite duplication, we know that we can change the color and the sprite frames. So the programmer's reference guide, if you remember just now, we looked at it and it said that the sprite frames, the sprite registers, can also be updated with a raster interrupt. Now, this code at the moment doesn't use interrupts. This code uses raster register polling to make sure that certain code is executed at the correct position on the screen. But we can also use raster-based interrupts. This is where the VIC chip will, when it reaches a certain raster position that we tell it, it will generate an interrupt flag. And that interrupt flag will, if the CPU is not in interrupt disabled mode, it will then start an IRQ, an interrupt request. And it will start an interrupt. And it will go through the interrupt handler, and then it will start the interrupt code. So luckily enough, the initialization code, the standard initialization library that I use, does all of the initialization and turns off all of the interrupts. It turns off all of the timers, it turns off all of the interrupt sources. It makes sure that the machine is in a default state that I know that all of the interrupts are disabled. And the machine is initialized to a good static known state, consistent known state, so that it makes writing code less guesswork and more certain. This initialization code here is also included in the standard library code, but you can see here it does all of the initialization that you need to get the machine into a consistent state. Very useful code, very well tried and tested, and it's all available for everyone to use because I put all of my Commodore 64 code in my GitHub repository. So let's update this code now so that it uses interrupts, raster timed interrupts. So first things that we need to do is that we need to basically just waste time in the main line. Just any code, any time in the execution which is not interrupt based, we'll just loop around in a very tight jump loop there. What we need to do is that we need to put the value of an address for the interrupt based code into not the IRQ service routine at 314 in hex. Because we've got the kernel turned off, we're not using the kernel interrupt handler, we'll you will override. Basically, the kernel is swapped out. We've got RAM sitting there now. So we will update the kernel IRQ service routine pointer. We'll update that in memory to point at our routine. In effect, by turning off the kernel and turning off BASIC, of course, we have taken over the entire machine. We're not relying on any of the kernel-based routines at all, so that we can safely poke into all of these VIC control or VIC registers and the interrupt control registers and everything else. We can safely use them all without needing to worry about behaving nicely with the vectors at 314 and 315 in hex. Okay, so we'll just set up the kernel IRQ service routine pointer. We'll poke a value, or store a value rather, into the raster register, which basically tells the interrupt chip that that's the raster position that we want an interrupt to occur at. And then we will put a 1 bit into the VIC2 interrupt control, so that bit 0, when it's set to 1, will start to generate raster interrupts, or rather raster interrupts are enabled. Every time a raster interrupt happens, we should really be acknowledging that the raster interrupt has happened as well, so we need to remember to do that. So after we tell the code to redirect the kernel IRQ service routine and then generate raster interrupts at a certain position and enable that raster interrupt source, we need to clear the interrupt status flag on the CPU so that then IRQs will actually happen, because when we're going through all of this initialization code, it actually enables it sets the interrupt flag, which disables the interrupts on the CPU. So now when you're running or when you're writing interrupt code, you've got the kernel disabled, so that you're using the kernel IRQ service routine vector itself. You need to remember to stack all of the registers and then restore all of the registers somewhere. You don't have to put them on a stack, you can put them in memory, but for readability purposes and maintainability purposes, we'll just put those registers on the stack. RTI will automatically return the status of the processor, so we don't need to worry about that, and it will also return from the interrupt, and it will return back to the main line, and there we go. We have a working first row for the raster interrupt. So what we can do now is that we can use the macro functionality of the assembler to create a couple of macros so that we don't have to duplicate this code for stacking and restoring the register values and doing a return from interrupt and RTI instruction. So we'll just make sure that we are using that macro now, and we'll also remember to use, of course, to include the raster IRQ macro as well, which does the appropriate stores. We'll also remember that we want to increment and correspondingly decrement the VIC2 border color register as well, just so that we can see what's happening. So there we go. We'll move those two macros. I usually put macros in a separate file, but for readability purposes, just this time, I'll put the macros up at the top of the source file. The macro definitions should be encountered by the assembler before you use the macro for the first time. Let's put an open brace in there. That was a bit of a typo. And there we go. The code still works. So now what we should do is that we should then, in the first row, we should tell it to run or to schedule a raster IRQ for the second row sprite. And we'll do that at the same raster position that we were doing it before. So we don't need to do a wait for raster now. We can get rid of the wait. We will include a new function now for doing a new label for a new function of running the second row code now. And what we need to do is that we need to include all of those macros for stacking and then popping the stack and then returning from interrupt as well, so we'll include that too. You don't have to stack all of the register values, of course. If you don't use the registers within the interrupt code itself, you don't need to store them. But if you don't store them, then when it returns from interrupt with the RTI instruction, then the code that was running outside of the interrupt will then have corrupted registers. So you need to make sure that you stack off or store somewhere and then just restore the correct register values, of course. So now we have first row code, we have the second row code. We'll just put an increment border color in what I like to call the main line, which is the code running outside of the interrupts. And you can see that the border color is being updated by the main line, but where the interrupts happen, we have these little bands of consistent flashing color, which appear broader or wider, if you like, or taller. And that's because the IRQ is stopping the mainline code from running as the IRQ does its update code. Okay. So anyway, we'll just increment the top left-hand byte of the screen memory to show that we have mainline code running in the background, but we have the interrupt code running on top of that. And that interrupt code now, we have the first row, we have the second row. And to really demonstrate a point, I think we can probably make a third row as well. So we'll have a third row, and the third row will be started from inside the second row. So the second row needs to point to the third row code there. We will run the third row interrupt code at raster position 160 should be adequate, right? And then we will start putting sprites at raster position 117. We'll also include a sprite Y position offset, and we'll also include sprite Y position offset for the second row as well. To really demonstrate the point, I think we'll change the X position and the spacing of the sprites in the second and third row as well. Let's just put them at sensible positions. There we go. So that's the third row. The third row, of course, loops back to the first row raster code. So that should all be fine. Where was the error? Value not defined, and the value is I. Ah, yes, there's the typo there. It should be .i, because .i is used inside the for loop. There we go. So now we have 8, 16, 24 sprites, all enabled, reusing the same 8 hardware sprites, but they have different positions, different colors, and different frames. So this is still sprite duplication, but it's sprite duplication using raster interrupts, raster IRQs, rather than just polling for the raster position. So the previous example code was showing sprite duplication. Now we'll start expanding this code by copying it to a new source file, and we'll start including what looks more like general purpose multiplexor code rather than just simple sprite based duplication. So just let me copy these source files around. We just add them to the project. We need to update the build it batch file as well to assemble the new source file, and then we'll update htwam3.a to make it look more like a multiplexor. So to make it look more like a multiplexor, we need to first create a few different tables where we have X positions, Y positions, sprite colors, and sprite frames. So let's make the necessary code changes to create those. The idea here is that we will have an interrupt up at the top of the screen to update the first 8 hardware sprites. But we need to figure out where we're then going to have the next bunch of sprites being updated. So we'll set up a label for a sensible number of maximum sprites, and we'll set that to be 16. I try and use labels as much as possible for numbers so that we don't have magic numbers floating around inside the code. It helps to make code easier to update or maintain, because if you want to change it from 16 sprites to 24 or 32 sprites, then we can do that just by changing a label rather than having to search and replace a whole bunch of magic numbers all over the place, right? So there we go, we have sprite X, sprite Y, sprite color, and sprite frame tables created in memory. Now we need to update the code to pull the sprite X, Y, color, and frame values from those tables rather than have hard-coded macros to update the sprite positions and frames and colors. So for starters, we need to have a raster based interrupt starting at raster line 20 this time, so starting up near the top of the border underneath the top of the screen border. We'll get rid of this macro based code here, and what we'll do is that we'll have a very simple loop which will loop through the first 8 values of those sprite position and color and frame tables and store those first 8 values into the first 8 hardware sprites, or all of the 8 hardware sprites in the VIC registers. So to be able to do this, we can just write a simple loop which updates the appropriate VIC sprite registers. So we've got VIC2 sprite 0x. You can see here the layout. So in their infinite wisdom, the X and Y positions are stored as pairs in memory, as opposed to having, sprite X position 0 to 7 and then sprite Y position 0 to 7. So we have to have, really annoyingly, an X register counter from 0 to 7, but we need to have the Y register counter increase from 0 to 2 to 4 to 8 to 16 in steps of 2 rather than in steps of 1. If we're doing it as coded loops, then that's what we have to do. Because we've got pairs of values that we need to update. Now, of course, this could be an unrolled loop, but I'm trying to make the code a little bit readable to begin with anyway. So we're using the X and the Y registers simultaneously to do this copy at this point in time. The sprite frame pointers are basically the default position for the sprite RAM plus the sprite frame screen offset, which is 03F8 in hex, if I remember rightly. So we copy from 0 to 7 and then exit the loop when we get to X register equal to the number of sprites. Now we could have had 8 in there, but 8 as a magic number is not very self-explanatory, right? It's a lot more self-explanatory to use the label for the maximum number of hardware sprites in the VIC. So this code here for the top of the screen raster interrupt should be fine. It should duplicate the functionality, but it should be reading. There we go. Now this is a good demonstration of why we need a general purpose multiplexer that knows about sprite Y position. And that's because the next interrupt coming along tried to update the sprite positions as the sprites were being drawn. You can see there, look, the top interrupt happens. The next interrupt along has just started to update the sprite registers in the middle of the sprites being displayed right there. And then this means that the sprites, as they're being displayed, their sprites get corrupted because they're not updating their positions correctly. We need to update the rest of the interrupt code now to read from the sprite table nicely and actually put the values into the sprite registers correctly at the right point. Okay, so the correct time to start updating sprite 0 is just after sprite 0 has completed its display on the screen. And we know where sprite hardware sprite 0 is because we can read the Y position of sprite 0 from the VIC chip back again. So then we know when the next safe point, the earliest safe point where we can schedule the next interrupt, is actually just underneath the bottom of hardware sprite 0. So that's what we will do as the start of this general purpose multiplexer. We need to remember the next sprite in the sprite table that we need to start processing. So we'll update that into a label. But we also need to know when we start the next interrupt, we need to know what hardware sprite we are going to update next. So the general purpose multiplexer's job is to remember the sprite table that it's reading, but also remember which is the next hardware sprite that needs to get updated. So we'll store those two appropriate values into appropriately named labels. And once I figure out the label naming convention that I want to use, I'll put the label name in there. Need to make sure that the raster position is correct, but we'll also get rid of the macro block of code for updating the next bunch of sprites. Now what we need to do is that this second row raster interrupt is going to be the raster interrupt code which updates the next hardware sprites as early as possible, just underneath when the hardware sprite has completed. So this needs to know the next sprite index, the next VIC hardware sprite index. It needs to know the next VIC hardware sprite that it's going to be using. But we also need to know when to schedule this interrupt. So we know that we're going to be updating hardware sprite 0 in the VIC next. So we just load its current Y position. We add on, so for example, 21. Now 21 is the height of a sprite, and then we can store that in the raster register. So we know that that's the earliest next position that we want to schedule the raster interrupt to happen. Remember that the sprite Y position table, as it's currently written, is sorted from smallest value to largest value, and that corresponds to the raster Y position register, where the raster Y position 0 is up at the top of the screen, and then at 255 it's just underneath the bottom edge of the bottom border of the screen. Finishing off the loop here so that the code reads in the next sprite data from the next sprite index that we want to process, and then copy over all of that information. You'll see that there's the increment X instruction and then 2 increment Y instructions, and that's because, of course, the X and Y position values in the VIC chip are stored as pairs. I really do wish the designers of the VIC chip stored them consecutively in memory, but there we go, never mind. So this code in the second row, it processes one sprite at a time, of course. Now, the logic here is that this interrupt for the second row is repeated for as many sprites as we need to display, and it will automatically use the next hardware sprite index in sequence. So the second row interrupt here is basically started with the first or sprite 0 in the hardware, in the VIC hardware, and then it will update its internal registers. It will do a check for the next safe Y position based on the particular hardware sprite that it should be updating next, and then it will do some suitable checks against the raster position, and it will decide whether or not it can schedule a new interrupt, or if it is appropriate to actually start updating that hardware sprite's registers at that particular point. So don't forget that as the code is running, the raster beam is steadily progressing down the screen in a regular timing fashion. There's nothing that we can do to stop really this raster beam progressing down the screen, so we have to keep on checking in the code to see where we are in terms of execution. The Commodore 64 and the video hardware regularly steals cycles from the CPU when it's updating its bad lines, for example, or when it's updating extra sprite information or data. So we have to take that into account. That's why we have to keep on testing regularly against what the raster position is doing. So this second row block of code here for the second part of the interrupt chain, if you like, basically has to keep on rechecking this information all the time. Also, a non-maskable interrupt could come along and interrupt the regular interrupts, and this also means that the code would need to keep on rechecking against where it is in terms of the raster beam drawing schedule. So at the moment, it's just reading already sorted values in the sprite tables for the X position and the Y position. Well, the Y positions are sorted, and the X position and the color table and the frame table all correspond to the Y position table. But the Y position table is already pre-sorted. There's no index table currently, and we'll see. And that's just to make the code a little bit simpler and easier to read and understand at this point in time. So I know once it's processed the hardware sprite, and the cats are running around and going crazy all of a sudden. Sorry about that. So I just know that this code has now processed a hardware sprite. So it's incremented Y twice, and then we have a little transfer Y to A and with 15, and then transfer A to Y. That safely then loops around to the next hardware sprite slot. So now we load the Y position for the next hardware sprite, and then we add on. In this case, we're going to add on 22 because that gives us a little bit of extra buffer beyond the bottom of the sprite. Now, these kind of things need to get tweaked for the code, depending on the level of optimization that you want. I've just used 22 here just to make sure that we are on the line really below the sprite, the bottom of the sprite as it's completed drawing, just for safety reasons. But you could make it 21 or 20 because there's actually going to be some lead-in time for the interrupt processing to happen for this code to run. So you can tweak all of these values depending on your comfort level and how much you want to optimize the sprite packing. But anyway, we know where the next sprite Y position is. So we calculate the bottom of that sprite. And if the current raster position has already progressed beyond the bottom of the next hardware sprite slot, we know it's safe to process the next hardware sprite. So we branch on carry clear back to safely processing the next hardware sprite slot. So we're still within the same second interrupt, or the second row interrupt code. We just loop around again, and then we start processing the next hardware sprite slot. However, if it's not safe to currently update the next hardware sprite information because the hardware sprite is still being rendered by the VIC chip, then we will then choose to start a new interrupt. We'll just save the new position. Actually, we'll save this here, and then we'll compare it there just to make the code nicely readable. You can, for example, change that so it's a reverse comparison, but I think that makes the code less readable and less understandable, so we'll keep it easier to understand, at least at this stage. Now, the full optimized multiplexor code uses reverse comparisons and lots of different mathematics to optimize the code flow, but it makes it harder to understand. So we'll just keep it nice and simple. So there we go. If the current raster position is greater than the next safe position for the sprite, then it loops around and it goes back to the safe to process sprite. Otherwise, we want to save by storing y back into the next sprite vic index. We also want to make sure that the next sprite index to process is also saved, so that the next time we get back into this code, it starts updating the correct positions. I've got some typos here. There we go. That should be max sprites, not the address of the sprite table. There we go. And there we have it. We can see all of these little white lines that indicate where the interrupts are occurring to update the sprites. So with this sprite formation, with the vertically offset or staggered sprite y coordinates, it's no surprise that we have lots of little interrupts occurring just underneath where each hardware sprite has completed rendering, because it then knows that it's safe to update the X and the Y positions and the colors and the sprite frame pointers for that hardware sprite that had just finished rendering. It would have been nice, wouldn't it, if the Vic chip would have generated an interrupt after completing rendering an optional interrupt after it finished rendering each sprite, but it doesn't, so that we just have to rely on raster-based interrupts to do this. We could, of course, use more complex maths to figure out a timer-based interrupt to trigger on a specific raster line, but we don't need to. We can use the raster interrupt functionality on the Vic chip quite nicely. So I'm just updating the sprite Y table here just to test out some of the sprite grouping. So I've got 8 sprites there, 4 of them at 50 and then 4 of them at 51 Y position. And then I'm going to have some regularly spaced sprites, basically 10 pixels between each sprite. 1, 2, 3, 4, 5, 6, 7, and then 8. These last 2 can be there, and there we go. I'm just making sure that the interrupt here occurs just after the sprites, and then just making sure that the sprite update logic is correct, and it is. I've got 8 sprites up at the top in the band there, and then I've got 1, 2, 3, 4, 5, 6, 7, 8 sprites underneath it. So it's definitely drawing 16 sprites, which is what I kind of expect, right? Based on the sprite Y tab. So that all looks pretty good. I mean, I'm just writing this code from scratch again, as you're seeing me type it in. So it's always nice to see when code like this runs practically first time. Now don't forget, I need to make sure at the moment that these values are sorted from top to bottom in terms of screen. There we go. Now, with this updated pattern of sprite Y positions, you can see here that there's a little black pixel gap there between the interrupts, and that's where there is a very small gap where the sprite Y positions have a gap in them, and it schedules a raster interrupt in the next 2 lines. Now, there are pros and cons between doing this, because while one of the interrupts completes, it allows the mainline code to run in the background. There is an overhead to storing all of the registers and then starting another interrupt in terms of spending the extra CPU cycles to start another interrupt. So there's a certain argument that goes that if it's going to start another interrupt and it's very, very close, in terms of time, you may not want to exit out of the interrupt. You may just want to perform a busy wait, for example. So all of these things, you can consider them in terms of your own personal optimization preferences, and then decide whether or not you want to spend extra cycles exiting an interrupt to then only enter an interrupt again on probably the next raster line or something like that. But it's personal preference. The optimized multiplexor code does these checks anyway, so that if the next raster line would have already occurred when the interrupt exit code would be executing, then it doesn't bother doing the interrupt exit. It just goes around and processes the next sprite straight away. It doesn't bother waiting. If I make the sprite too tall by updating this value to 26, for example, you can see that it flickers, and it flickers because the sprite Y positions don't allow, because they're too tight for the next hardware sprite to be chosen. So I'm just making sure that the routine behaves in an expected way in that instance. But the sprites aren't 26 pixels tall, so it's okay. Basically, I was checking to make sure that if the sprites were too tall or too tightly packed, then the code doesn't have time to schedule the next raster position. Now, there are certain checks that can be done, of course, in a full, more general purpose multiplexer. You can avoid trying to draw a sprite if drawing that sprite would result in the hardware sprite registers overflowing, or if it's too late to start updating the next sprite, you just ignore it for that frame and you hop over it. And that basically this is what the bunching check did in the fully optimized multiplexer, was that it was checking to make sure that you didn't have more than 8 hardware sprites in a horizontal band, and it would just ignore any extra sprites that would cause these kind of like timing overflows. But in this simpler multiplexer code, I'm not going to add too many optimizations like that because it makes it too complex. And there are other topics to get into in terms of sprite sorting and stuff like that. But I think what we can do is that we can add a little simple check in terms of the next safe position being very close in terms of time, just as an example, which is what this code here is going to do. Just thinking about it. So taking the next safe position, subtracting the raster, and then comparing it with 2. And then if it's greater than 2 raster lines, or 2 pixels vertically, then it's not close. So then go to the not close time label and then schedule the next raster interrupt. Otherwise, we can do a quick wait for the raster position to be more than or equal to the next safe position, or conversely, while the raster position is less than the next safe position, then loop around in this quick wait function, and for visual identification purposes we'll be incrementing the border color, and then once it is safe to do so, then we can just jump back to the safe to process sprite routine here, so we know now that the raster position is greater than or equal to the next safe position after that quick wait function. So the quick wait is just basically a very short busy wait. Just adding some code comments here just to really clarify the intent. There we go. So if we run this now, we should see that we get an incrementing flashing border indicating that a busy wait has happened. We still have the same correct number of sprites on the screen, don't we? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes, we do. But we have a busy wait happening, and that busy wait is going to be happening there. Let's get rid of the increment border color now because flashing colors are not too great to look at. But we can see now that instead of that empty black pixel line, that line is the line, the pixel, the color for the interrupt now is continuous. There's no break. It's not rescheduling a new interrupt. It's continuing on the same interrupt, and it's just doing that quick wait function. So this is the kind of code that you can add to avoid exiting and then rescheduling or restarting a new interrupt. It's just a little quick example there. If we comment out that code by using pling if 0, comment out the block, and then there we go. We've got the old behavior back again now, where the interrupt completes and then a new interrupt is scheduled a couple of lines below the exit of the current interrupt. Instead of acknowledging the raster IRQ has happened at the beginning of the interrupt when it occurs, I want to acknowledge the raster IRQ has happened just before setting the next raster position interrupt. So I'm going to change the code around now to do that, to alter where the raster acknowledge happens. So I want to acknowledge the raster IRQ, and then I want to schedule the next IRQ by storing into the VIC2 raster register. And there we go. I just want to make the code a little bit more obvious and not hide the IRQ acknowledge in the macro. I want to change the code so it's a little bit more obvious and transparent in what it's doing there. So the code still works, which is great. It's always nice to see when the code still works. 8, 9, 10, 11, 12, 13, 14, 15, 16. So we still have 16 sprites. They all look different, and the colors look different as well, and consistent with what I would expect to see. So I think now what we should do is that we should add a whole bunch of more sprites just to make the sprite pattern more complex. So right down near the bottom of the screen, I'm going to add another row of 8 sprites just to really make sure, really exercise the multiplexor's hardware sprite reuse logic. And there we go. Expected execution is successful here. Just counting it, I think we have 16 sprites now. Yes, looks like 16 sprites. Sorry, 24 sprites. Right, so that all looks good. Let's just change the Y position a little bit. I just want to see if I can expand the ordering of these sprites. That looks okay, doesn't it? Let's run the code in C64 debug GUI so that we can use the VIC raster debugger here just to see what we're doing. We can also use the zoomed in screen display here just to really show where the sprites are. Of course we know where the sprites are because we're writing a sprite multiplexer, but it's always nice to see that the code works in a different emulator as well. When developing code, it's actually quite important to use different emulators. Now I tend to use Vice most often these days, but in the old days I used to use C64. I used to use Hox as well sometimes for some things. Hox used to be better at drive code debugging in terms of cycle accuracy, and actually I still think it probably is. I mean, Vice treats drive code cycle accuracy a little bit less accurately than Hox still. Hox has that nice functionality where you can actually single step a machine clock cycle as opposed to just stepping an instruction. And stepping clock cycles sometimes is really, really useful. So sometimes I still use Hox for debugging purposes. But it's nice to be able to visualize here the raster beam as I go down the screen and moving it back up again, basically rewinding time. It's nice to see the pattern of hardware sprites that get updated here as the raster beam travels down the screen. And it's really good to see that it's behaving in an expected way in terms of updating hardware sprites just after they have finished rendering. So you can see here that after that whole horizontal row of sprites there has finished rendering, it then chooses, because the code is constructed in that way, to then update the whole chunk of the next 6 or 8 sprites very, very quickly. And that's because it can, because the horizontal band of 6 or 8 sprites, or whatever it was, had just finished rendering. I want to clarify this code here and make it a little bit easier to read. So I'm going to alter the way in which the next Vic sprite index value is updated in the Y register. So instead of having a multiplied by 2 value in this label, I'm going to have it go from sprite 0 to 7 so that I can use the index directly in the color and the frame pointers, or the color register and the frame pointers, but then I want to multiply it by 2 so that I can use it to update the X and the Y coordinates for each hardware sprite. So I'm just doing an increment Y, the load Y with next sprite index. And now I can AND it with 7 to make this value cycle around from 0 to 7. Of course, I need to transfer Y to A so that I can AND it with 7 and then store it into the next Vic sprite index, and then I can multiply it by 2 again and then transfer the accumulator to Y so that then I can reload the current sprite Y position. There's more optimal ways of doing this, but we'll just leave it like that for now. The code is more readable rather than trying to completely over-optimize the code and make it harder to understand. But of course, there are much more optimal ways of doing this kind of thing. For example, we could have completely unrolled interrupt blocks of code which specifically update each hardware sprite without using indexed addressing, for example. And that's what the optimized sprite multiplexor code does. It uses more memory, but it removes the need to maintain an index register for the indexed memory loads and stores. But basically, I'm tweaking the way that the index for the hardware sprite register is maintained because I know that I need to start updating the code for using sorted values. And when using sorted values, it's going to be important to use an index value. And we'll get onto that in a minute when we get onto the sorting code. But here I'm just making sure that the visible, already sorted sprite positions in the sprite table there are still rendering correctly, and it looks like they are, right? Everything looks good still? I think so. I can optimize this a little bit by moving that code up there so it only does it once, and that's because if I loop around back to safe to process sprite, I know that the Y register already holds or contains the next hardware sprite index into the VIC chip registers. I already know that it's multiplied by 2 in all of the code paths, so I can safely move that multiply by 2 code out to the start of a potential loop. It's not always looping, you see. Sometimes it will loop in the case of this wide interrupt there, which is updating more than one sprite. But I know that the interrupt just underneath it is probably only updating one sprite. So the number of iterations through this sprite update loop is indeterminate until actually the code is executing at a particular point on the screen and how it corresponds to the current raster position. Okay, so it can always vary. It's not consistent. I mean, you could predict it to within a certain degree, but it really does depend on the interaction of the VIC chip raster Y position and the cycles that are being used for the code at that particular point in time, and how many cycles the VIC chip has been stealing for bad lines and Sprite DMA access and all of that kind of stuff. So it really does vary. And also if there's a non-maskable interrupt running, whether or not you want to play samples, for example, or if you want to use a non-maskable interrupt for a screen color split or something like that. All of these factors mean that there is a certain degree of variability in this code. So let's just change the X positions here. I just want to have a look at a more tightly packed formation of sprites in terms of horizontal position. I just want to make sure that it still all looks good. Now, I don't see any flickering sprites, which is a good sign. Let's change it to a different, let's change it back again to how it was. That still looks good as well. I'm just checking visually here how good the routine looks. Let's put it back to there again. Yeah, so this is like a waterfall or a cascade of sprites, right? They're very tightly packed horizontally. Just really double checking this code here for sanity. I think it's all good. Just really double checking that everything I've got running here is good. I mean, visually it looks good. I'm just really double checking the logic flow of the code here. My brain is just pondering different things just to make sure that everything looks good. Before we get on to the next stage of the code, just tidying up the comments. It's no longer multiplied by 2. Being able to assemble the code and rapidly iterate by running it in an emulator is a really comfortable way, an easy way or easier way of developing code. So let's get on to the next stage, where we need to talk about sprite multiplexing and sorting. Now, the sprite multiplexer works best when it knows that the sprites are sorted from top to bottom. And that's because the raster beam moves from top to bottom in the screen. So if the sprites are sorted, then you know with confidence that you know where the next safe Y position to update the hardware sprite registers is. So we need to add in sorting. But before we just do that, let's just use a little unrolled block of code here to update the first row of sprites, because it's not really optimal to use a couple of index registers to do all of that copying. It's possible to get rid of the index registers for doing the copy and actually just use what we call an unrolled loop. So the unrolled loop is just basically what, you can call it speed code or optimized code if you like, but basically it uses a bit of extra memory space for the code, but it removes all of the increment x, decrement y, decrement x, and comparison with x or y and branch and all equal stuff, right? We're removing, freeing up the index registers, because we know actually that when we start using an index table for the sprites, now when you're sorting, instead of sorting by y and swapping the y coordinates and also swapping the associated x coordinate and the color and the frame, instead of swapping all of those extra values when you're sorting the table, you only need to really swap the index table values and then use the values in the index table to reference into the x and the y positions and the colors and the frame pointers without needing to update all of that extra information. So you're only swapping 2 values. You're not swapping 4, 5, 6, 7, 8 values depending on the parameters for each sprite. Now, if your index table has values that go from 0 to 15 or 0 to 23, then you can use the index value in the index table to then index into the sprites tables, and then you can also sort by the index table. Now, the advantage of this is that if you do not reinitialize the index table between frame to frame, then basically you're using the previous results of the sort to improve the time taken for the next frame or the current frame, because you don't have to redo all of the work. You basically use the advantage of using the previous results of the sort in your next frames by not reinitializing the table. As long as your table is initialized once at the beginning, and as long as you don't corrupt the values in memory or anything like that, then you should be okay. So we need to also update the second interrupt to use the index table. So we have the next sprite index to process. We then use that to load the sprite index that we actually really want to read from the index table. So we're doing an indexed read by using an index table, but it makes the overall sort a lot quicker. So it's a pro and con thing again. If you want to really optimize tight, very fast to execute interrupt for this multiplexer, then you would need to not have an index table and you would read from the already sorted table. But then that means that your sort gets more complex. And if your sort is more complex, then you need to have more time for a sort later on. So there are certain pros and cons in optimizing this so that you optimize for the thing which takes up more time, which is actually going to be the sort. Now I've got a little bug there. That should be the sprite index table comma x, and then it does a transfer a to x. And then, there we go. Now we're using an index table. We still get the same visual representation of the multiplexed sprites. So now we know that we're good to actually start sorting by the index table and implementing a sort routine for this multiplexer. Now, a good place to do a sort is after the multiplexer has finished all of its interrupts. And we know when the multiplexer has finished doing all of its interrupts is when it starts the top row again. Starts the first interrupt chain. Okay, starts the top interrupt. So we'll start adding a sort routine right here. The first sort routine that we'll implement is going to be a relatively simple bubble sort. So we're going to be sorting, of course, by reading the y values, but by indexing the y values from the sprite index table. Now, the characteristics of a bubble sort is that you have to go through all of the values, and if any of them are out of order, then you do a swap. And then you flag that you've had to do at least one swap. And if after processing all of the values that you want to sort, at the end of that loop, at the end of that first pass code, if you have detected that you've done a swap, you have to go around again and then check to make sure that that all of the values are in order. And if they are in order, you don't swap and then you exit. But if they are not in order and you've done a swap, you need to keep on going around until you have not done a swap. This is a very simple implementation of a bubble sort. It's called a bubble sort because the values gradually bubble into the correct order. They move around and they swap around until the values are sorted in ascending or descending order. We want a stable sort so we should really be checking for greater than or equal to. So if it's greater than or equal to, then we do not want to do a swap. We only really want to do a swap when one value is less than the other one, okay? And we want to make sure that we are sorting in ascending order. So we'll have an appropriate sort loop here. This is the start of the loop. We're taking the two index table values, and then we're using those index table values to then index into the y tables. So we're loading the accumulator with one y position, and then we're comparing the accumulator with the other y position. Okay, we're using the x register as the index value, and we're using the y position as the index into the table itself, into the total number of elements to be sorted. So we'll just put this there, and then what we need to do now is that we already have Now we just need to swap the two values, right? In the index table itself. So we swap the values in sprite index table +1 and sprite index table, and we swap those two with respect to the index y. Okay, so these are the two values, and then we just need to do the swap. So let's put the code in for the swap. So we'll read in one value, and we'll make the code, we'll keep the code readable. So we'll not use a very optimal way of doing it, but what we will do is it will push the accumulator onto the stack, and then load the other value and store it into the relevant index, and then pull the old value from the stack and then store it into the other index. So with 1, 2, 3, 4, 5, 6 instructions, we swap two values over and then store them back in. Again, it's not optimal, but it's certainly just one way of doing it. Just completing the code here for the loop. So we need to compare with the number of elements that we have. And we need to branch around. Just branch back up to the sort loop 1, of course. Just before the sort routine begins, let's color the border red. And when the sort routine completes, we'll change the border color back to black, I think, to indicate that the sort routine has finished. Actually, we won't set it to red explicitly. We'll just do an increment border color, and then I think we'll just do a decrement border color here. Now, because the border color should already be white, incrementing it should go to the next color along, which should be red anyway. We need to check for the changed flag, and if it's been changed, in other words, that it contains a non-zero value, we go back and do the sort. Now, because it's already sorted, the red raster time here is quite short. I mean, it's processing, 24 elements. So let's just try incrementing the sprite Y tab. So we'll increment and decrement two different sprite Y positions, and we can see, well, we have some flickering going on. Why is that flickering happening? Well, we'll have to debug that in a second, but we can see that we actually get something moving around, which is a good first pass attempt. Let's try decrementing a different sprite. There we go. Okay, we still have a little bit of flickering going on. We'll figure out why that flickering is happening in a second. Let's just increment one sprite Y position to begin with, not update two Y positions. We'll just see what happens with one. Okay, that's not too bad. And then, well, when that sprite Y position went to the bottom of the screen, it seemed to use an awful lot of time, didn't it, for the sort? The red time was quite large. But we also have a sprite overflow situation. So let's make the sprite Y positions a little bit more regularly spaced so that we don't have 8 hardware sprites in a horizontal band and making everything far too busy, because I was trying to move a sprite from the top, which already has 8 hardware sprites in a horizontal band, to the bottom band, which also had 8 hardware sprites. So let's make them more regularly spaced. That's better, but we still have this flicker happening when the sprite reaches the bottom of the frame. That might be because the sprites are not too tightly packed. I don't think so, but we'll just test that. And that's because, so the sprite Y position, of course, goes too far up to the top of the screen, of course. Okay, so we need to guard against the next raster position being calculated to be too far up the screen. So don't forget, the first raster interrupt occurs at line 20, and it takes 4 or 5 or 6 or 8 lines. So if we're then reading the sprite Y position, which could be 0, and then adding on 22, the raster interrupt is not going to trigger at the right time because the raster has already passed. So we need to make sure that we don't try and trigger the next raster interrupt earlier than, say, for example, the top of the screen, top of the border of the screen. And that's where the next sprite could, in theory, start becoming visible. So we'll compare the next raster interrupt trigger position to be greater than or equal to the top of the border of the screen. Okay, and if it is, then it's okay. If it's not, then we'll clamp that position to be the minimum position that we can schedule the next raster interrupt for. So now the second interrupt will not occur earlier, so that gets rid of some of the flicker, but it's still not quite good, is it? It's still flickering when the top sprite moves to the bottom. So let's advance one frame at a time. This is the great thing about using an emulator, is that you can pause it and then advance one frame at a time. I'm just counting the number of sprites here, and it seems to be okay up at the top of the screen. You can see that the red raster time is growing when the sprite moves and reorders itself, so that it is doing swaps. So it's there we go. Aha! Well, we have a whole bunch of red raster time there, and it's flowing off the bottom of the screen, and wow, it's going halfway down into the next frame. Which is no good, right? So when the sprite moves from the bottom to the top of the screen, the sprite has to bubble backwards all the way through the sorted list of values all the way back again, and that's apparently taking a huge amount of time. So a bubble sort is not great when things are, or at least when one sprite is getting very out of order compared to all of the other sprites. So bubble sort is not optimal. So what can we do? Well, we can try and optimize this routine, right? And that's what we'll do now, is that we'll try and optimize it by removing one of the indexed loop registers. The expensive part is going to be this swap, of course, but also updating the Y register for the maximum number of sprites is also going to get quite expensive too. The swap is expensive because we're having to push the value onto the stack and then pull it from the stack. Oh yeah, there's a little bug here. So I just noticed that it should be -2, not -1, and that's because we're pulling out pairs of values, so we don't want to pull the last value from beyond the end of the table. So that was a little oopsie. It still doesn't help the excessive raster time being used at the end where the sprite moves from the bottom to the top of the screen again. So I still think that we need to optimize. If I single step each frame, I still think that, yeah, we still need to optimize this bubble sort so that it is not so inefficient. So I think that's what we'll do now, is that we'll leave the code there. I think we'll just comment it out, but we'll write a more optimized version of this piece of code which does a slightly more optimized bubble sort. First of all, let's change the number of sprites back to 16 so that we can hopefully update in one frame without having that end of frame flicker, so that we can see that the time taken is still quite excessive, but it is not causing an interrupt overflow, and it's not causing a flicker. So now that we've got a good basis of time, let's comment out this code here, and we'll then take what was there, but we'll get rid of this loop. And the way that we can do that is that we can use the pling 4 or exclamation mark 4 directive to unroll this loop and then not use an index Y register. Okay, so we'll have the same kind of structure so that we'll have a changed flag, okay, but we'll get rid of the Y register. So this is where we can load X with a specific index table value. So we'll use the same kind of thing before. We'll get the label .I equal to .ii minus 1, so that then we get a value from 0 to 15 or 0 to 23 or whatever the max sprites is. Actually, it should be, max sprites minus 2, right? So we still need to read from the index table, but we can use the X and the Y registers now directly. Now, the reason why we're going to be using the X and the Y registers is that then when it comes to doing a sort, we don't need to stack and swap. Or when we do the swap, we don't need to stack and swap the values around and store them. We can just do a swapped over store X and Y, okay, because we already have the values in the X and the Y register. We're using the accumulator to load and compare the Y position for the sprite, okay, but the X and the Y index values don't get overridden. We have them from the load X and the load Y, so that's great. So we just do a swapped over store. And so there's no pushing and popping onto the stack, which is a lot quicker. We still need to increment the changed flag, but now we just need to update this code here so that it works. And then we need to, of course, have a do sort label as like the other code did. And then we need to check the change flag outside the end of this unrolled piece of code. Okay, so because it's inside a for loop, the label has already been defined, and that's because the local label is already in the context of the code. So we have to, we're doing a forward reference, you see. So we'll just change this code to use a forward reference rather than a forward reference label. So we'll get rid of the label here, and we'll just put a branch on carry set to plus, and then we'll put plus here, which is forward anonymous branch point, if you like. We've loaded with the change flag, and if it's equal to, it just branches over. But if it's not equal, in other words, it's a non-zero value, then it goes back and does the sort. This is a bit quicker than the sort using index values. There's less red raster time being used, but to be honest, it's still quite excessive raster time for a sort. And again, this just really clarifies that using a bubble sort, even an unrolled bubble sort, is a little bit inefficient. An understatement. It's very inefficient, actually. So we'll optimize this code a little bit further by using a technique called a Gnome sort. So we'll comment out this code and we'll copy it, and we will paste a new version, and we'll have an unrolled version with the backwards check. So the Gnome sort basically is somewhat similar to a bubble sort, but where a swap happens, if a swap happens, then it will go back one index. Rather than flagging that there has been a change, we'll move back one index and then do a recomparison to make sure that the just swapped value doesn't need to be swapped again with the previous index. And this way, we are basically progressively sorting one element at a time, but without flagging without flagging a change has happened, and without needing to rescan the whole table over and over again. So we need to know that if there is a previous value, then we need to jump back to it. Now, because there's no index values being used for the loop index, because it's unrolled, we can actually just jump to the previous block of unrolled code in memory, because each block of unrolled code is itself accessing a particular index within the sorted tables. So going back to the code here, we just need to know, I've got an end of file assembly error there, and that's because I was missing, it's telling me that I was missing a brace somewhere, and I was. There we go. Right, okie dokie. So that should, in theory, let's cross fingers and hope it should work. And with 24 sprites, you can see now, wow, isn't that a dramatic improvement in terms of the red raster time being used for the sort? So the Gnome sort method is actually very optimal when the loop is unrolled. So this Gnome sort method is quite well known. Let's see if I can find the Wikipedia page for it. The Gnome sort is also implemented in my standard library of standard library routines. The Gnome sort is used in the optimized multiplexor. There's a whole bunch of macros there to unroll the code for specific numbers of sorted elements. The Gnome sort itself is actually tested with my automated testing framework for testing 6502 code and other behavior as well. So the standard library is pretty well and pretty comprehensively tested. So we have, or we should be able to find the Wikipedia page for the Gnome sort, and we can have a look at the pseudocode implementation for the Gnome sort. Just searching it up. Here we are. If I remember rightly, this page has there we go, pseudocode. So we can see here it starts at the first position. Now this uses an index, but if you're using an unrolled piece of code, you don't need to maintain the index pointer. You just go back. So there we go. It's done a swap, and if it's done a swap, it goes to the previous position. If it doesn't need to do a swap, it advances to the next position. And so with an unrolled piece of code, with an unrolled loop, you just jump back to the previous chunk of code, which is exactly what this does. And there we go. So we have a nicely optimized sort now using the Gnome sort method in hopefully what should be a relatively easier to understand piece of Sprite multiplexor code. And like I say, it's not completely optimized. But over-optimization means that the code is harder to read and understand, so I prefer to keep it less optimized so that it's easier to understand. But yeah, hopefully this should serve as a useful example of how to write a multiplexor. It's not the only way on how to write a Sprite multiplexor, but it is certainly one way of writing a multiplexor. I think the most important thing is knowing when to update the hardware sprites. So using this kind of external IDE cross-assembly or cross-assembling or cross-compilation, but assembling, and then running it in an emulator and using more mature debugging tools really helps the development process. So when I'm debugging code, often I like to have source code level debugging for my code. So you can see here I'm using the Vice PDB monitor to connect to the emulator as it's running, and then I can actually see all of the code. I can see how the code looks like when it is executing the unrolled version within this pling4 assembler directive for unrolling the code or repeating blocks of code. I can step through line by line in the source code for the sort routine. I can see what registers are being, what the register values are and how they're being updated. I can see what memory is being accessed and all sorts of things. So it's very useful to have these kind of like tools when you're developing code. I can have the emulator screen view open side by side with the source code view, with the disassembly view. I can single step things. I can set breakpoints. I can see the disassembly view along with the source code view side by side in the same window. So I can verify that the assembled code resembles the source code. I can turn off the source code view and I can just look at the disassembly view. I can do all sorts of things. I can disassemble a range of code in memory, so I can disassemble a large proportion of the unrolled Gnome sort, for example. I can unroll, or I can disassemble all sorts of great stuff in the memory, and I can use this source code view to also show large amounts of memory or disassembly. Let's increase the number of animating sprites that are falling down the screen, just to really test the multiplexor and its sort code. So there we go, we have 3 sprites falling down the screen. It still seems to operate quite optimally, considering it's relatively quickly written code. It's actually behaving quite well. I'm really quite pleased, and it's not heavily optimized or anything, and it's still working relatively well. It's always nice to see, isn't it, when code works well, relatively, first time, relatively speaking. Let's change the x coordinates so that the difference, so we have a different nice falling cascade of sprites. You'll notice that as the sprites move down the screen, the color and the order of the sprites generally don't change. Of course, and you would hope that they don't, because you're not updating all of the sprites, you're only updating some of the positions of the sprites, right? You want all of the other sprites to maintain their consistent coloring and their consistent frame usage, of course. Let's add even more vertically moving sprites. Let's change every 5 sprites, I suppose. Let's do that. Let's make some sprites move quicker than others as well, just to really test the sort routine and the sprite multiplexor. There we go. It's still working. Isn't that fantastic? You might notice here that these sprite priorities are changing as sprites fall down the screen. Now this is normal, and that's because as sprites move vertically, we have different sprite priorities or different numbers of sprites being used up above those sprites, so that when the hardware sprite index cycles around from 0 to 7, sometimes that 0 to 7 cycle around point will occur at different vertical positions on the screen, because we were using a different number of hardware sprites up above. So that's why you get this altering priority display between the different sprites when they're overlapping like this. Don't forget, in this video I will be adding a link to the debugging notes and also all of the source code used in this video, so that you can use all of this source code and all of this information yourself in your own projects. So there we have it. I think that's the end of this how to write a sprite multiplexor video. I hope that you found this deep technical dive into sprite multiplexing on the Commodore 64 useful, and if you like these kind of videos, then I hope you would consider liking or subscribing to this channel, so I know that you like this kind of stuff, and I really hope to catch you around next time. I want to thank all of my supporters and the donations to this account. You are the Raster interrupt to my sprite multiplexor. So thank you very much for watching. Take care, have a great day, evening or night, wherever you are.